For the convenience of the people who couldn't join us today or who want to review this webinar, I am recording this webinar too so that we can provide you the YouTube link of the recording. So today we'll talk about solid structure interaction in Midas Civil, and we'll talk about the general aspect of solid structure interaction. Why is it required? Why is it required for big bridges? Why is it required for integral bridges? And we will see later during the session, we will see how you can use Midas Civil to perform solid structure interaction. So first of all, what is solid structure interaction? Now, when we talk about bridge design, we always try to concentrate ourselves on the superstructure design, but that's not it. The purpose of constructing any bridge or any structure whatsoever is to transfer the loads successfully from one location to another. So if you talk about any bridge, the purpose of the bridge is to transfer the dead loads into the ground, to transfer the vehicular load into the ground. And since it involves the transfer of load from the structure to the soil, we need to have an understanding of how the structure interacts with the soil. And the science behind this is known as solid structure interaction. Now, there are several textbook definitions that I could have talked about here, but the most simple definition, the simplest of all that I could find, was the way structure interacts with the soil is called solid structure interaction. It's very simple and self-explanatory. So as I said, all structures include safe and sound transfer of load from the structure to the ground, and the amount of load transferred through each foundation depends on the location of the foundation in the structure, the flexibility of the foundation, and the behavior of soil where the support is applied. So basically, the load distribution on the bridge deck, the load distribution on the foundation, it depends on if the foundation is flexible or rigid, where the foundation is located, and what is the behavior of the soil where the foundation is. So this way, we need to understand all these phenomena when we design the bridges. Now, these phenomena, they are important in some bridges and they are not very important in other bridges, but they always exist in all type of bridges. Now let's study the load transfer mechanism of integral bridges. Here I'm going to talk about the vehicular load. So as you can see here, the wheel load is first transferred by flexure in deck to axial forces in pier and integral abutment, and then it is transferred to the soil. So this is the load transfer mechanism of the integral bridges. The wheel load through flexure is transferred by deck to the support system, which can either be the abutment or the pier, and then it is transferred to the soil. So this is how the load is transferred by the integral bridges. If you talk about suspension bridges, the load is first transferred from flexure in deck to axial force in the hanger. Then it creates a tension in the main cable, which results in compression of the pylons, and this is how the load is transferred to the soil or the ground. So this is the load transfer mechanism for the suspension bridges. So whatever bridges we design, all the bridge include the transfer of load from one location to another, and the first location would be the deck and the last location would be the soil. And how the load is transferred, we need to study that, and in this particular seminar we'll see how the structure behaves with the soil, how it interacts with the soil. So once again, as I said earlier, I have been saying this thing quite a while in this webinar. The purpose of the bridge is to transfer the vehicular load safely from the structure to the ground, and it is important because if you have two exactly same bridges, they can have different load distribution if they are constructed in soils having different properties. So two exact same bridges, they have the exact same dimensions, they have the exact same geometry, pre-stressing. If it is a pre-stressed bridge, exactly same pre-stressing, but they can have different load distribution if they are constructed in soils having different properties. Now, if you perform solid structure interaction, it gives you more confidence on the design since the parameters are not assumed but they are obtained after performing analysis, and the design that we perform after we perform the solid structure interaction is less conservative and hence it is more economical. So these are some of the factors why we need to perform solid structure interaction in integral bridges. Now let's see, why do we need to perform solid structure interaction, especially for integral bridges? Now these are the type of bridges which are widely constructed. That's why this would be the topic of my seminar today. I'm just going to talk about the solid structure interaction in integral bridges and how you can perform analysis on integral bridges in Midas Civil. So first of all, it is required to understand the science behind the solid structure interaction in integral bridges. For geotechnical engineers, it is required to understand how the soil abutment will behave to the effect of creep, shrinkage, and the thermal changes. And for structural engineers, it is required to estimate the secondary effects of creep, shrinkage, and temperature changes on the superstructure itself. So if you distinguish yourself as a structural engineer, you need to understand, you need to estimate the secondary effect of thermal changes and creep and shrinkage of the concrete deck on the superstructure. And if you are a geotechnical engineer, you would be interested on how the soil or the abutment will interact with each other. Now let me compare the two bridges. One of them is integral bridge, another is simply supported single span bridge, and let us see if the temperature increases, what would be the effect on these two structures. So as you can see on the left hand side, let's say the temperature increases. Now if the bridge is simply supported, what will happen is it will expand and there would be no thermal stresses generated in the structure because it is allowed to expand freely, so there would be no additional stresses. But when it comes to integral bridges, let's say the temperature increases. Now what will happen is these abutments, which are integral or you can say rigidly connected to the deck, they would restrain the movement of the deck in the outward direction. So basically it prevents the expansion of the superstructure, and this way it leads to secondary effects. And this is what we should study. When it comes to creep and shrinkage, what happens is the bridge tries to shrink or it tries to contract. Now once again, if you have a simply supported structure, it will simply contract and you would not have any additional stresses. But when you have an integral bridge, it restrains, the abutment restrains the bridge to contract. So this way it induces secondary forces, and that's why we need to understand the behavior, the mechanism of how the abutment interacts with the deck. The same is the case with the pier. If you model the pier supports, the results can be different from the case when you do not model the pier supports. Generally what we do is we just apply a fixed support at the base of the pier and we just perform the analysis to obtain the design results in the superstructure, at the pier cap and the pier itself, and this way we design the structure. But the results can be substantially different if you model the support beneath the pier. And once again, if you have different type of soils, the results that you obtain for the design or the deflection results that you obtain, it can be substantially different. And I have done a comparison between different type of soil, and I'm going to share that comparison with you later on. So here we have seen that we need to make sure that we study the solid structure interaction for any type of bridge. So wherever it is possible and practical to do the solid structure interaction, we should try to do the solid structure interaction. But the question is how we can do the solid structure interaction. So there are two methods by which you can do the solid structure interaction. The first method is model the actual soil surrounding the foundation and the abutment. So this way what you are doing is you are modeling the entire soil which is covering the foundation or the abutments, and this way when you perform the analysis, the solid structure interaction will be automatically performed. The second way to do solid structure interaction is to model the soil supports using representative springs. So what you can do is, instead of modeling the entire soil mass, you can represent the soil using several springs that simulates the soil behavior. So here, this is method 1. The method 1 actually makes the model too complex, but it is very real. The kind of analysis results that you would obtain from this model would be very realistic, and you would obtain a precision that would be of the order of, that would be very high. But it's not very practical, because we don't want our finite element models or our analysis models to be so big that it takes days and months to run the analysis. So method 2 is more practical. It gives you reasonably good results, and it helps you to understand how the load will be transferred from the superstructure into the soil. And hence, in this seminar, we are going to learn how you can actually do method 2 in finite element analysis software like Midas Civil. Now, let us first understand how we can simulate the soil supports in abutments. Now, if you see any abutment, whether it is an integral abutment bridge or it is just a simple abutment where the bridge superstructure rests on the top of it through bearings, in any type of abutment systems, you will see that there is a soil mass behind the abutment, and this soil mass actually applies some sort of trapezoidal load onto the abutment, and on the other face of the abutment it has nothing. So basically, if you apply the load from the free face of the abutment towards the soil will resist that load, and if you apply some additional load from the soil side towards the abutment, there would be no soil at the free face, so it would not restrain that load. So that's why, in order to simulate this kind of situation, what we do is we apply these spring supports at the face of the abutment where the soil is, and these spring supports are compression only. So basically what we are doing is, if you apply a load from the free face of the abutment, these springs will be activated and they will restrain the structure. But when you apply the load from other end, since they are compression only, they would not affect the analysis. So if the force is passive, the springs will be activated, and if it is active, the springs will not be activated. Now let's see how we can simulate the soil springs for the piles. Now if you see the piles, when we design the piles, we design the piles either using skin friction, or the load bearing piles could be either skin friction piles, or they can also be end bearing piles. Now to model the end bearing pile, it's very simple. You can apply the base spring here and then you can perform the analysis. But when we define a skin friction pile, then it becomes important that we apply the spring at all the locations throughout the length of the pile, so that we can study how the axial force is being taken at several intervals of the pile. So here what we will do is we will apply 3 sets of springs. So these 3 sets of springs will be, the first spring will be base spring, which would be the end bearing spring. Then we would have springs that would laterally apply the support to the pile. So as you can see here, this is the pile, and here if it goes in the left direction, this spring will get activated and it will restrain that deformation or deflection, and if it goes towards the right, this spring, these all springs will get activated and they will not allow the movement of the pile towards the right direction. So this way, when we model the springs for the piles, we model 2 compression only springs for both sides. But what we can do is we don't have to model 2 compression only springs. What we can do is we can just model 1 spring which have both the stiffness in the positive and the negative direction. So even if it goes towards left or right, it has the same stiffness, and this way we can model the soil springs for the piles. The third type of springs are the springs which would cater the skin friction, and as you can see here, these springs are in the gravity direction and they allow any vertical deflection on the pile. So this way the pile springs are modeled, and if you study the PY curve of soil, you would realize that it is linear up to a certain extent and then it becomes non-linear. So when we define these lateral supports, these lateral springs, we modify this, we create this behavior and we apply the springs that have these nonlinear characteristics. Now these nonlinear characteristics, they can affect the analysis to a greater extent, and you can, I mean, if you guys work for rail bridges, you would know that the ballast, it also has these kind of characteristics, and when we perform analysis on those type of bridges, we need to make sure that these type of behavior is simulated. And similarly, this type of behavior has to be simulated when you are performing any kind of analysis for doing the solid structure interaction. And at the same time, when you perform the pushover analysis to obtain the capacity of the bridge, this type of nonlinear behavior of the soil has to be considered because it changes the pushover curve or the performance curve, and the code specifies that you need to take into account the nonlinear characteristic of the soil. Now this is how the integral bridge is modeled as opposed to a bridge which is simply supported. Here you can see that to model the integral abutment bridge, we have certain springs which restrain the abutment laterally, and then we have springs which provide support to the piles, or if we have a raft, these kind of springs are used to support it. So this is how the modeling, the support modeling of integral bridges is different from the simply supported bridges. Now let us study how we model these kind of springs in Midas Civil. Now I have told you how you can model the springs to perform analysis on piles and abutment, but the real question now is what spring constant should be used. Now the spring constant, it is defined in several codes, and you can choose any code and then you can apply the spring constants, but generally the structural engineers, for defining the pile springs, they use Matlock and Resi formulae, which is embedded into Midas Civil, and then you can automatically obtain these spring constants from Midas Civil. And at the same time, you can also apply the abutment springs in Midas Civil using the automated feature. Now, to study how the springs are applied in Midas Civil, I've shown you the theory behind it, and then we will see how we can apply the springs to the abutment. So here you can see when you want to model the spring supports for the abutment, let's say that this is the abutment which has these tubing walls, and I want to apply soil supports to this abutment. So what I'll do is I'll go to the integral bridge support feature in Midas Civil, and I'll ask the program to apply the abutment springs for me, and based on the geometric data of the abutment and the soil data, it will apply the soil springs for me. And it will apply two types of soil springs. The first type would be the compression only springs, which would provide the passive support by the backfill, and it will also apply the support to the footing. So basically the abutment is resting on the soil. So the bottom fiber of the abutment, it will have certain upward reaction from the soil, and to model that reaction, we use the springs that are applied on the bottom nodes of the abutment. So this is how the abutment springs are modeled by Midas Civil. Now let's see the theory behind it, how the abutment springs are modeled. So as I said earlier, these are the compression only springs, and these springs here, they represent the upward reaction of the soil. And these springs are calculated based on the thermal changes, and whatever thermal change that you define in the dialog box for defining the abutment springs, Midas Civil will automatically calculate the spring constants for you, and based on the differential temperature and the total bridge length, it will apply the spring supports for you. The most important item that we should understand here while we perform the solid structure interaction in any finite element analysis software is how accurately we model the pile springs. And that is why we have several theories out there which talks about how you can model the soil springs. But in Midas Civil, as I said earlier, we have embedded the Matlock and Resi formulae, which will automatically apply the soil springs for you. And as you can see here, you need to enter the spring data. So what you will do is you will enter the soil type, the ground level, the pile diameter, the unit weight of soil, the earth pressure coefficient at rest, coefficient of subgrade reaction, internal friction angle, and the initial soil modulus. And once you define all these parameters, select the piles and and Midas Civil will automatically compute the soil spring supports for you, and it will apply the soil spring supports for you. Now, some of you might be confused about what are these parameters, because being a structural engineer myself, I learned about these factors when I was in the university, but now they are difficult to recall. So what we can do is, the structural engineers, they can always talk to geotechnical engineers and they can obtain this data from the geotechnical engineer. So you can just ask them, what is the unit weight of soil, what is the earth pressure coefficient at rest, the coefficient of subgrade reaction, internal friction angle, and initial soil modulus, and once they supply you these items, you can use Midas Civil to automatically generate the springs for the piles. And as I said earlier, it will apply a lateral restraint. So as you can see here, this restraint, these springs in blue, they will have a lateral restraint, and then the vertical springs will be modeled adjacent to the pile, so that you can take into account the skin friction of the soil. And this is how these springs are generated in Midas Civil. As I said earlier, they are based on Matlock and Resi formulae, and there are several, thousands of equations that this guy has used to determine the springs constant. And as you can see here, it has a nonlinear behavior. So this is how the spring constants are generated. And if you want to obtain more information on what exactly this method is, you can refer to any textbook. And since this is not the scope of this webinar today, I'm going to skip this part. So I'm just giving you a hint that these are several equations that this method uses, and the parameters that you defined in the previous slide, they will be used here to generate these nonlinear behavior. And it's not a rocket science. Once you punch in these equations from Excel sheet, you can also obtain the spring constants from the Excel, which you can put into any finite element analysis software to perform the soil structure interaction. But in Midas Civil, just to make your life a little easier, we have embedded these equations in our software so that you can perform the soil structure interaction without losing much time and data by bringing in equations from Excel sheet to the software. So as you can see here, this is how the springs are generated. It has a nonlinear behavior, and these three locations, they can be obtained from here, and this way Midas Civil will automatically determine the nonlinear springs for you. Now, as I said earlier, I'm going to compare the different type of supports that I have applied to the pier cap, and we will apply a lateral load as well as a load in the gravity direction, and we will study what is the deformation for three different soils. So as you can see here, the first soil will be soft clay, the second soil will be stiff clay, and the third soil will be sand. And all the other parameters like pile diameter and the ground level will be same, and they will differ in coefficient of subgrade reaction and the internal friction angle. So I'm going to use Midas Civil, and I'm going to define these three parameters on the pier, on the piles, and we will see how the deformation changes. So let me now open Midas Civil in front of you so that I can do this parametric analysis between two different type of soils. So first of all, I'm going to show you the model in which I have no soil. So I'm opening up that model in which I have no soil. Just give me a second. So here in this model, I have applied the supports and loads and everything prior to this webinar. So I'm just going to show you the results. But before that, I'm still going to show you how the springs are defined. So here it is. I hope you can now see this model in Midas Civil. It's a line beam model, and it represents a pier and a pier cap. And here you can see, if I show you the supports are applied at the base of the pier. It's a fixed support, and I have applied these nodal loads. So here you can see this is how the nodal loads are applied, and I have certain gravity loads as well as the loads in the global X direction, and we will see how the deformation changes with this profile and the soil profile. Now let me show you one of the models in which I have applied the soil support. So this is the pier model again. It is the same pier model, and here I have modeled the actual support. Just to give you some information about this particular project, this is a project which was done by one of our clients, and as you can see here, this is a skewed bridge. You can make that out by just looking at the support. Here you can see the support is not aligned with the pier because it is a skewed bridge. And in this particular model, instead of applying a fixed support, I have applied these soil supports, as you can see here. So if I go to display here, you can see the skin friction springs that have been applied. And to show you how the lateral springs are defined, I'll just go to properties here. And here you can see a multilinear type of point spring is defined to simulate that behavior of the soil. And these parameters, these numbers here, they are automatically calculated by the Matplotlib and Resi formulae, which is embedded into the software. And to define that, I just go to boundary, integral bridge, and I go to pile springs, and this way I can define the parameters, and the springs will be automatically generated by the program. You are not restricted to Midas Civil to do this kind of analysis. Once again, if you have any other finite element analysis software, you can model this kind of behavior, but the most challenging task would be to model the soil springs. In Midas Civil, as I said, these springs can be automatically generated. Now let's see what is the deformation in these two models, and we will also show you the clay models. So this is the comparison table for these four type of models, and here you can see the deformation for the pier cap top in the X, Y, and Z direction. So if there is no soil, if we apply a fixed support at the base of the pier, this is the deformation in the X direction. The deformation reduces if you have sand, because the sand would provide more stiffer support. So here you can see the deformation reduces, but the deformation shoots up when you have a soft and stiff clay in your model. So as you can see here, it's a 10-time difference if you have clay in your model. So this way you get to know that if you model the foundation, the results can be significantly different. And this is an actual comparison that I have done based on the real soil parameters. And here you can see like there is a 10 times difference in the deformations. The deformations for the Z direction would be more or less the same, but when it comes to lateral direction, like global X or Y direction, in which the earthquake when the earthquake hits the bridges, it always deforms in like majority in the X and the Y direction. And as you can see here, modeling the soil can make a difference. So now we will open a new project in Midas Civil, and we will apply the soil supports, and we will perform soil structure interaction in Midas Civil itself. Now those of you who have already installed Midas Civil on their computers, please open Midas Civil, and I'm gonna follow some steps on the screen, and then you can follow those steps on your computer itself so that you can learn how Midas Civil can be used to model to perform soil structure interaction. So let me open the start model here. I hope you guys already have the start model with you. So please open Midas Civil and open the start model. So as you can see here, this is how the start model looks like. And here you can see I have applied the supports are not applied here. So I'm just going to use the integral bridge feature to apply the support. But before that, let me talk about this bridge for a while. Okay, so it's a steel composite structure, and to perform analysis on a steel composite structure, it is evident that we perform the analysis for the stage when the concrete has not hardened and the section is still non-composite section. So for this particular bridge structure, we have modeled two different construction stages. And the two different construction stages would, the first one would be the non-composite stage, and the second one would be the composite stage. And these are the framing plans of this particular bridge model. It has 5 steel girders and a concrete deck on the top of it. and this is how the elevation looks like. And since this in Midas Civil it's a 3D finite element analysis software, you can model this type of elevation difference between the two abutments, and that is exactly I have done in the model. Now once you open Midas Civil, you can let me walk you through how this model is created and what are the different definitions in this model. So when you open Midas Civil, on the left hand side you see something known as works tree. So under the tree menu you have this works tree, and from this works tree you can see what are the different type of materials, time dependent materials, cross sections, loads and boundary defined in this model. So here if you click on plus sign in front of material, you can see 3 materials are defined. You can also see the time dependent materials that are defined. You can see the different cross sections which are defined. You can see, okay, just to talk about the cross section, in Midas Civil we have a composite cross section where you can define the steel girder and the concrete deck on the top of it at the same time. So as you can see here, it's a 2-part cross section, and you have defined the steel girder and the concrete deck on the top of it, and then you can tell the program when the steel girder is activated and when the concrete deck is activated. If you want to see the loads, you can just go to the load definition, and then you can right click and see the different loads that you have applied on the structure. And in this particular bridge model, I have applied 7 different type of loads. I have applied the self-weight, which includes the self-weight of all the elements in the model. The wet concrete load is modeled to ensure that the condition when the wet concrete has not hardened, the wet concrete load will be taken by the steel girder itself. So to model that situation, we have defined the wet concrete load. The scaffolding load is modeled. The scaffolding load during the concrete pouring, and the barrier load is modeled. Then we have modeled certain system temperature. The temperature of the entire system is increased by 30 degrees to obtain what would be the effect on the structure. And we have also modeled the temperature gradient, where the temperature changes along the depth of the cross section. And this is how I have modeled the temperature gradient. Here you can see how the temperature changes along the cross section, and this is how it is defined. Now before I show you the construction stages, let me take you to Midas Civil itself, and let me show you how you can walk through the works tree to see the different definitions in the model. So this is the integral bridge model that you have in Midas Civil. I hope everybody, those who have installed Midas Civil on their computer, they can see it. So you can see the materials, the time dependent materials. As I said earlier, we need to study what would be the effect of a creep and shrinkage of the deck onto the bridge. So that's why I have defined the creep and shrinkage parameters as per CBFIP code, which is considered to be the most practical. And here, if you want to use the AASHTO code, you can also use the AASHTO code. Similarly, I have simulated how the compressive strength changes with time. So when you see the creep and shrinkage, what happens is, first you cast the concrete, then the concrete shrinks a little, it induces secondary stresses in the entire structure, and then after quite a while creep starts acting, and then again the secondary forces are induced in the structure. So to model this behavior, I have defined the creep and shrinkage parameters, and these 4 cross sections are defined. If I show you the cross section properties for the composite section that I've used, this is how the cross section properties are defined. Then if you want to see the self-weight, the loads, they are defined like this. You can right click and go to display, and you can obtain the loads. And here you can also see that I have performed the moving load analysis to obtain the effect of moving load onto the truck. Now, one of the good things when you model the substructure for the integral bridges is you can obtain the effect of moving loads onto the substructure. So here, when you move the truck on the superstructure, you can obtain the effect of moving truck onto the substructure that we will see later during the seminar. So now let us see the different construction stages for this particular bridge. To change the construction stage, you can change from here. You can change the base to stage 1 to see how the abutments have been constructed in this stage. In the stage 2, the girders are installed. So as you can see here, the steel girders are installed, and you can see the cross frames are also installed. So in this stage, the wet concrete load will be activated like this, so that we can obtain the effect of the case when the section is non-composite and the wet concrete load is acting on the structure. And in stage 3, the cross section becomes composite, and you see the concrete deck onto the top of steel girders. So this way, this particular bridge has been modeled in Midas Civil. For those who are following me with the tutorial, they can also obtain how the construction stages can be changed from in Midas Civil, and this is the tutorial that I have prepared for you. Here I have shown you how you can change the construction stages. So change stage 1 to stage 2 and stage 3 to see how the stages are modeled. The stages are important to model in any bridge structure because the stress history would be captured when you model the construction stages. So think about this particular stage when the entire wet concrete load is being taken by the steel girders. So what happens is, when you calculate the deformation or whatever stresses that you obtain for this stage, they would be inside the structure throughout the bridge life. And if you do not perform construction stage analysis, you cannot obtain the stress history as such. So now let us define the soil supports. To define the soil support, these are the 2 layers of soil that I would like to model in the bridge that we have. So first of all, we will model 2 layers of soil. The one is sand, one is clay, and to model the soil supports for the abutment, we will use the backfill properties. And these properties I have already provided to you in the tutorial, and I'm also going to demonstrate to you how you can apply the soil supports right now. So first of all, we will go to boundary integral bridges, and we will select the boundary group as supports, and we will apply the support to the integral bridge, and we will define these parameters. So now let me open Midas Civil once again in front of you, and I'm gonna apply the soil supports in front of you. So once again, for those who are following me, please open Midas Civil and open this particular model. It says SSI start, and then we will define the soil supports. So first of all, to make any modifications, you need to go to the base stage, and then you can define the soil supports. Okay, so to define the soil supports, first I'll go to boundary integral bridges. I will select the boundary group name as supports, and I'll go to abutment spring, and I will select the elements. So I'm going to select the left abutment first. To select the left abutment, I have many options in Midas Civil. So what I'm going to do is I'm just going to click on this button, which is select single. And before actually I select from the 3D view, what I can do is I can change the view to 2D, which looks like this, and then I can easily select these abutment elements. So as you can see here, once you change the view from 3D to 2D, you can easily select the abutment elements. Now after you select the abutment elements, they will appear here, and now you will select the nodes for the footing. So the nodes, as I said, they have to be at the bottom of the abutment. So this way you select the nodes. Then you define the abutment height, which is 13 feet in this case, the abutment width, which is 59 feet, and the total deck length, which is 123 feet. The void ratio for the soil, the differential temperature, whatever differential temperature for the site classes, you can put it here. And then you define the strip footing data. What is the foundation width? 3 feet. The foundation bearing pressure, so whatever foundation bearing pressure is, you can put it here. And once you click on apply, Midas Civil will automatically apply the abutment supports for you. So as you can see here, I clicked on apply, and these supports are automatically modeled. Now let us model the support for the abutment on the right. For that, I'm going to select the abutment elements one more time. So as you can see here, the abutment elements are modeled or are selected, and now I'm going to change the direction from normal positive to normal negative, because as I said, the springs that we generate here, they have to be compression only springs, and that's why we are changing the direction here. Now I'm going to select the nodes for the footing. So I'm going to select the nodes at the bottom of this abutment this time, and all the parameters remain the same because essentially the abutment looks the same. And once we click on apply, Midas Civil will automatically apply the abutment supports in this model. So the people who are following me in this tutorial, please follow these steps and define the abutment springs for both the abutments in this model. Okay, so as you can see here in the works tree now, the abutment springs are modeled, and now we will go ahead and we will model the pile springs. So I'm just going to wait for like a minute here so that the people who are following me in this tutorial, they can catch me up and they can model the springs. So once again, you can change the view from 3D to 2D view by clicking on this option, and then you can easily select all the abutment elements and whatever type of elements you want to select. Okay, now let's just move ahead and see how we can apply the pile spring supports. So this is the tutorial that you have to follow. Now to define the pile spring supports, we will again go to the integral bridge boundary feature, and this time we will select the pile elements and the pile spring, and we will define these parameters. So as I said earlier, as I've already shown you, the piles are embedded in two different types of soil. So we will model 2 layers of soil in this particular example. So let me open Midas Civil one more time, the same model that we have been working on. I'll go to the side view, I'll go to boundary, integral bridge, I'll select pile springs, and I will punch in the data. First of all, it has to be sand. I'll click on the ground level and I'll put the ground level at the base of abutment here. The pile diameter would be 2 feet, and I'll put in the unit weight of soil, the earth pressure coefficient at rest, the coefficient of subgrade reaction, the internal friction angle, and now I'm going to select the pile elements. So as you can see here, the pile elements and the nodes are selected depending on the soil layer. Let's say you have a soil layer between these two elements. So what you can do is you can divide the element into 2 and then you can apply the supports. So once I click on apply, you can see these springs are generated by Midas Civil, and now we will apply the support to the bottom part of pile, which is embedded into clay. So I'm going to select the clay part here, and it's going to be a soft clay. The pile diameter would be 2 feet again, and I'm going to define these required parameters that you can obtain easily from the geotechnical engineers. And once you click on apply, you will see that all the soil supports are applied to the piles. And here, this is how the soil supports look like. The compression tension springs, they are only for the abutment. The linear springs are for the abutment as well as the piles, and the multilinear springs, they represent how the soil is laterally supporting the piles. So if I go to properties here, I can obtain how the soil springs are defined. So this way it completes modeling the soil supports. And you can see in the construction stage number 1, where I activated the abutments, you can see here that the supports are activated, which implies that I have activated all the soil springs in the first stage. Now we will see what are the results that we can obtain from this model. So I'm going to wait for 1 minute again so that the people who are following me in this tutorial, they can catch me up, and then we will talk about the results in this particular bridge model. So as I said, the supports are automatically defined in the construction stage number 1. So when you when you define the group as supports, this group is automatically activated in stage 1, because when I created the model, I just put it here. Just to talk about this particular dialog box here, in this construction stage, in the compose construction stage dialog box, you can activate the elements which appear in the construction stages. You can activate or deactivate the boundaries, and you can activate and deactivate the loads. Now let's go ahead and perform the analysis in this model. So we will perform the analysis, and this will perform static analysis, construction stage analysis considering the time dependent material behavior for concrete, and we will perform the moving load analysis and thermal analysis, and then we will obtain the results. So I have created these several pages of results that you can review from the model, but in this particular webinar I'm just going to show you different results that I have obtained for this model. So the analysis is complete. We will obtain the results for this particular model. So let's just go to stage 2 when the steel girder appears, when the steel girders are installed, and let's see the deformation in this stage. So I'll go to this deformation contour, I'll check on the legend, and I'll click on apply, and it will show me how the deformation is. So here you can see that when the wet concrete load is applied, the deformation in all the girders is almost uniform, but when it comes to high skewed bridges and when it comes to curved bridges, we need to make sure that the deformations are under range here, and the sufficient load is being transferred by these cross frames. So as you can see here, this is the stage 2. Then you can go ahead, and if you want to obtain the forces in stage 3, you can go to stage 3 and obtain the forces, and this is the deformation in stage 3, and this deformation caters the composite cross-section properties. Now if I want to obtain the forces, I can go to result, forces, beam diagrams, and let's just go to stage 2 and let us obtain the bending moment diagram for this stage. So this is how the bending moment diagram looks like in this particular stage. In stage 3 itself, the wet concrete has hardened, but you won't see any appreciable negative bending moment because, as I said earlier, the program remembers the stress history. The wet concrete load is applied onto the steel girders only, and this is the bending moment profile of the steel girders. Now let us see the actual force on the pile. For that we will go to FX. Now this is the actual force on the pile. As you can see here, the actual force on the pile, it decreases with depth. So the skin friction, it takes considerable portion of axial load at each interval, and then the pile axial force, it reduces with depth. If you want to obtain the forces in the abutment itself, just go to forces, plate forces moment, because the abutment is a shell element, and then you can obtain what type of forces you want to see. Let's say I want to obtain the bending due to dead load only, and it shows me how the bending moment looks like for the dead load. Now let's see the effect of creep and shrinkage. So to obtain the secondary effect of creep and shrinkage, I'll go to CS creep secondary, and let us obtain the effect on the girders. So I'm going to go to beam diagrams, and let's see what is the effect on the girder. So here you can see some additional axial force which is generated due to the creep secondary. If you want to obtain the bending moment, this is the additional bending moment generated due to creep secondary over the time. Now let's see what is the effect of thermal changes onto the bridge. To obtain the effect of thermal changes, I'll just go to result, forces, beam diagrams one more time. This time I'm going to select the system temperature load, where we have increased the load of entire system by 30 degrees, and I'll obtain the axial force, and this is how the axial force looks like in the bridge track. As I said earlier, if it were a simply supported structure, it would have been allowed to expand and there would be no stresses, but you can see here that these additional stresses, they appear in the bridge structure. Now if you want to obtain the axial force due to temperature gradient, you can select temperature gradient and you can obtain the axial force due to temperature gradient. And similarly, you can obtain the bending moment diagram and the shear force diagram based on that. But generally for thermal loadings, we just consider the axial forces. That's why I've shown you the axial forces. Now let us see the effect of moving load. To obtain the maximum, the moving load envelope for the hogging bending moment, I'll go to MVmin, and this way it shows me the hogging bending moment at the abutment location. So as I said earlier, when we install the cross frames and the steel girders, it shows you a simply supported bending moment profile. Then you apply the wet concrete load on the top of it. The concrete hardens eventually, and then it becomes a rigid connection at the abutment and the deck. And when you perform the moving load analysis after this particular bridge has been fully constructed, you will obtain the negative or hogging bending moment at these locations. So this is how you obtain the results. Now, if you want to obtain the shear forces and stuff like that for moving loads, you can obtain that in integral abutment bridge using Midas Civil. So you can obtain either maximum hogging bending moment, maximum sagging bending moment envelopes like that. So all in all, Midas Civil, you can use Midas Civil, you can use the process that I've shown you right now to model and analyze all sorts of integral abutment bridges. It is not restricted to single span integral abutment bridges, but if you want to analyze multi-span integral abutment bridges, you can do that in Midas Civil. At the same time, you can do steel bridges as well as precast I-girder integral abutment bridges in Midas Civil. Now I'll go to the second part of this webinar, in which I'm going to talk about how you can use Midas Civil for precast I-girder bridges, and then we will see how you can use Midas Civil to automatically design the substructure. Now, as I said, it is good to obtain the forces, the effect of forces, and how the structure interacts with the soil and the foundation. But at the same time, we should be able to design them too. And that's why in Midas Civil we have provided several design features that would help you to design the pier cap and the piers as well as the pile. So now I would request you all who are following me in this tutorial to open the model named Precast I Start in Midas Civil. So I'll also open this model. Okay. So this is the model, the precast I-girder bridge. As you can see here, it's a two-span continuous structure, and if I show you the top view, you will see that there are 7 girders in the first span and there are 6 girders in the second span, and you can see there is a 20-degree skew on the second span. So this is how this bridge has been modeled in Midas Civil. And before we actually define the supports, let me walk you through the different elements that have been defined in this particular bridge. So we have 3 different materials. We have time-dependent materials, we have different cross sections that have been used, and then we have different supports that have been defined in this particular model. So going back to the tutorial, you can walk through the works tree to see the different definitions for materials, time-dependent material, cross-section, etc. And here you can see, you can go to works tree and you can obtain the different loads. Now in this particular model, the client wanted to obtain the effect of concrete pouring onto the structure, and that's why you can see the 2 wet concrete loads here. So we modeled all the construction stages considering the pouring sequence for the concrete, and this way we will obtain the results for the same. And we also have applied pre-stressing tendons, and the barrier load is also applied. Now to see the construction stages, here you can change the construction stage to substructure from base, and you will see that the substructure has been constructed and activated in this model. And then you can go to different construction stages, and here you can see how the bridge has been modeled. Now let me go to Midas Civil itself, and let me demonstrate to you how this particular construction staging has been done. So if you want to obtain the tendons, you can just right click and go to display, and it displays the 3D tendons for you. In Midas Civil you can define the tendons in 3D, and if I zoom in at this location, you can see how the tendons are defined. You can define as many tendons as you want in Midas Civil. And now let me show you the construction stages. So stage 1, the substructure is constructed. Then stage 2, the span 1 girder is installed like this. Then stage 3, the span 2 girders are installed, and now the wet concrete will be poured on the top of these girders. So deck 1 wet concrete. So here, if I show you, this is how the wet concrete load is defined. Then in the next stage, the deck 1 becomes composite. So now you will see the deck on the top of this particular part. So as you can see here, the deck 1 part has become composite, and now the wet concrete load is applied onto the remaining structure and it becomes composite. So this way you can simulate these kind of concrete pouring sequence in Midas Civil, and you can obtain the effect for the same. Now, without wasting any further time, let me just demonstrate to you how you can design the substructure. The superstructure can be designed, but since we are focusing on the foundation and stuff in this particular in this seminar, I'm going to show you how you can design them. So if you want to design, let's say, the pier cap, I'll select the elements of the pier cap, and then I'll go to design, ASHTO LRFD 2012 design. I'll go to reinforced concrete design, and I'll go to concrete coat design, beam design, and here you can see it shows me the design, and you can also obtain a graphical report showing what is the reinforcement required, what are the different checks, and this way you can check the capacity of the pier cap. Similarly, you can design the piers. So I'm selecting the pier elements here, and I'll go to reinforced concrete design and column design, and this way it's going to design the pier for you. And when it designs the pier, it checks the PM interaction curve. It tells you what is the reinforcement required and stuff like that, and based on the PM interaction curve, it automatically generates, as per the code, it will check whether the pier is safe or not. So it checks all these moments and axial forces, and based on the PM interaction curve, it makes sure that the pier is safe. So this way, after performing the analysis on integral abutment bridges, or after performing the solid structure interaction on any bridge type, you can basically design those elements in Midas Civil. So I already have supplied this tutorial to you. You can follow the steps in this tutorial, and you can apply the soil spring supports, and then you can perform the analysis to obtain the results for the same. I'm sorry, I think I went up to 1 hour. So I'll quickly talk about how you can perform seismic analysis considering the soil structure interaction. If you see the seismic design criteria for the ASHTO LRFD code, it says that for the structures in STCD, you need to consider the foundation flexibility effect, not only in obtaining the demand in terms of in the event of an earthquake, but you need to obtain the capacity considering the soil structure interaction or the foundation flexibility effect. So here, this is the clause from the code. Section 4.8 talks about the foundation flexibility effect, and here you can see how the results can be different if you consider the foundation flexibility effect. And here I'm gonna present this case study in front of you. Here you can see these two separate cases. In the first case, the pier is modeled with a stiff support at the base of the pier. So basically all the rotations and translations are restricted at the base of the pier, and then we obtained the demand, which came out to be approximately 3 inches. And when you consider the foundation flexibility approach by modeling the foundation in Midas Civil, then you can obtain the demand, which could be much higher than what you obtain from the without modeling the support. So that is the foundation flexibility effect that you can see here. This is the foundation flexibility effect. And once you obtain the capacity after performing the pushover analysis, the capacity is still affected by the soil that you have modeled. So here you can see the pushover curve in the x direction. Basically, the structure becomes more flexible when you model the foundation, because as I said, the foundation itself is flexible, so it doesn't lead to more cost, but actually in a way it reduces the cost and it leads to design optimization. When you apply a fixed support at the bottom of the pier, what you are doing is you are doing an over conservative design, because as I said earlier, when you perform the soil structure interaction, you have more confidence on how the structure is going to behave. And not only for static analysis, this condition is true for seismic analysis also. And the people who are joining us from the West Coast, they must know this thing because they are doing this thing day in, day out. And this in this particular software Midas Civil, since you can model the foundation, you can take into account the foundation flexibility effect, not only in obtaining the demand, but also the capacity in the event of an earthquake. So this is how it helps the seismic, the solid structure interaction helps in static analysis, because when you model the foundation and stuff, you can obtain the effect of moving load on the foundation as well as the abutments, etc. You can obtain the secondary effect due to thermal changes and the creep and shrinkage. Secondary effects can be obtained from after performing analysis. And if you are performing seismic design, you can obtain the demand and the capacity considering the foundation. So this is, so basically, if you perform solid structure interaction, whatever concrete that you are putting into the bridge, you are modeling it, and this way it leads to better understanding of how the structure is going to behave. And on this note, I would be ending this session. And before I actually end it, I just want to tell you one more thing. If you are following the conventional approach, that is designing the superstructure first and then giving the forces to the geotechnical engineer and he does the foundation design for you, you can still follow that practice. You can still follow the existing tools that you have to design the superstructure. But when you do the design, considering the solid structure interaction, considering how the non-rigid behavior at the ends where the abutments are rigidly connected to the deck would affect your structure, you can be more confident about your design, and basically you can optimize your design, which is the need of the hour. So on this note, I would be ending this webinar, but before we actually go, let me take up questions from the people here. So if you have any question, please put in, and here I'll just read all the questions from people and I'll try to answer all the questions in real time here. And for your convenience, I have put in my name and my phone number on the screen. So if you want to discuss anything in details, please let me know. Okay, now there is a question by Brian. The question is, can we input the H files? Yes, we can input the H files in Midas Civil, and we have this built-in database of several pile cross sections that you can use, and this way you can model the H files in Midas Civil. Let me quickly demonstrate to you how the H files can be modeled. So when you go to section properties, here you can select the database, and then HP files can be modeled. So this way you can model the H files in Midas Civil, and our clients, they have been designing structures with H files. There is a question from Michael Roberts. The question is, what is KH? KH is the earth pressure coefficient at rest, and so basically Ka is active, Kp is passive, and Kh would be it's a geotechnical parameters, and you can obtain these values from the geotechnical engineer, but theoretically it is 1 minus sine phi, the internal friction angle, divided by 1 plus sine phi. So this is how we obtain the Kh, and it's going to be the passive one. Now there is one question by Kidas. The question is, he asks whether in Midas Civil we can have multiple strata of soil. Yes, in Midas Civil you can have multiple strata of soil, and you can obtain the soil springs. Now there is one question by Joel. The question is, why would the earth pressure coefficient be the same for all three soil types? I have just assumed these, generally the earth pressure coefficient, it would be a little different for different type of soils. That's why I used 0.45 for the clay, but for the sand I used 0.4. So it was, for the clay it was 0.45 in the actual model, and the one in which I have used the same, it was just for the demonstration purpose, because I just wanted to tell you how the soil type can change the effect on the bridge. So I kept all the parameters same, but I just wanted to make sure that only the soil type is different, because when we obtain the spring stiffness, it depends on what type of soils that we have in the model. Now there is one question by Jordan. The question is, how can you model pile springs when your soil properties change at a given depth? Now, as I said, as I've already demonstrated to you, you can model several layers of soil by selecting different pile elements and defining different type of soils to it. So this way you can consider the different type of soil layers in Midas Civil. So once again, if you guys have any questions, please put in your questions and I will answer your questions during the, we still have about 15 minutes left, so I'm going to answer your question during the session. Now there is a question by, I guess 3 people asked the same question. The question is, how can the fixed support yield lesser displacement when you have modeled the soil, the soil. So in one of the examples, when I compared the deflection between several models, you would have seen that the fixed support yields lesser, more deflection than the case when the sand support was. So basically, when you apply the fixed support, you just apply the support at the base of the pier, which is a single node. But when you are modeling the actual foundation, then we consider that the entire area of the pier, it is connected to the foundation, which leads in lesser deformation. And that's why you obtain lower deformation when you have the foundation model. So once again, when you model the stick beam or the pier, when you model it using a beam element, when you apply a support just at the bottom, it has a fixed support only at one location. But when you are modeling the area element, then you apply the restraint to all those nodes at that location, and this way you obtain lesser deformation. I hope I have answered your question. Now, there are several other questions that I would like to take here. As you can see here, there are questions like, why is the pile axial force applied in a uniform distribution? It should be different for different soil types. Now, the pile force, the load that you apply on the pile, it can be, I mean, based on your experience, you can apply whatever load you want to apply on the pile. In the model that I have demonstrated to you, I did not apply any load on the pile, but depending, I mean, if you want to apply any additional load on the pile, you can do that. Also at the abutment, I did not apply the trapezoidal force, but you can apply the trapezoidal force on the abutment to study the effect. Now, there is one question by Mr. Joel. The question is, how are pile group effects accounted for by Midas? Do you need to apply P multipliers or they are automatically applied? Now, when you are applying soil supports using the automated feature in Midas Civil, basically the Matlock and Resi formally, it applies the soil springs, but it does not consider the pile group effects. So you can say that it is ignored, but yes, you can apply certain modifiers that would help you to take into account the pile group behavior. There is one question by Mr. Ben Zhang. The question is, could the user input the user-defined PY curve? Yes, you can also put in the user-defined PY curve. You can define your own springs, and this way you can perform the analysis. There is another question by Blake. The question is, will Midas Civil design pre-stressed concrete piles? Midas Civil can be used to analyze and design pre-stressed concrete piles as well, and at the same time, if you have a pre-stressed piers, you can use Midas Civil for those analysis too. Another question by Juni. The question is, can Midas model the elastomeric bearings? Yes, Midas Civil can be used to model the elastomeric bearings too. Let me just quickly go to one of the models here that I have for the elastomeric bearings. So this is a model, and here you can see these links that I have used here, which connects the pier cap with the girder. These links here, these links represent the elastomeric bearings. So you can model the bearings in Midas Civil very easily, and then you can obtain the bearing forces, and this way you can basically obtain the design forces for the bearings. Now there is another question by Venkata. The question is, can we find the lateral capacity of piles and settlement etc. in this approach by modeling the soil springs similar to the use of various geotechnical equations? Well, the settlement, it's an external phenomena. It is not inherent to any model. It is something which comes with time. So when you want to obtain the effect of settlement, you can perform the settlement analysis, which would be a separate analysis from the structure analysis. So that kind of analysis can be done automatically in Midas Civil. You can just punch in what would be the total settlement of the structure, and then you can obtain the effect on the superstructure as well as the substructure. So settlement is a different science again. It is not included in this webinar, and since it's an external phenomenon, it has to be manually defined by the user. There is another question by Robin. The question is, the soil springs at abutment wall should have different stiffness at the edges and the corner. Yes, that's right. The stiffness would be different if you have an edge spring or a spring at the middle, and Midas Civil does handle it automatically. Now there is a question by Peter Phillips. The question is, Midas Civil does not allow moving load analysis with non-linear springs. Generally, when you perform the moving load analysis, we try that our structure remains in the linear range, and that's why we do not have this option. But generally for moving load analysis, nobody goes into the non-linear range, because if you think about it, it is a little impractical approach, because generally the bearings or the pile springs, we just keep them elastic under the moving load analysis. Now there is another question by Peter Phillips. The question is, can Midas Civil model different ground lines on both sides of abutment walls? Yes, Midas Civil can be used to model different ground lines on both sides of abutment walls, but I haven't never seen that kind of scenario, because generally we bring in the soil and then we compact it behind the abutment. We just compact it. So this kind, you can still do that in Midas, but I cannot think of a scenario where we have used it, but yes, you can do that. There is another question by Ben. The question is, how did you model the steel beam elements and cross frames? In Midas Civil, you can model the steel beam elements. I used the composite section for that, and to connect the cross frames with the steel girders, I used rigid links so that they can transfer the forces. Now there is another question by Scott. The question is, are nonlinear effects in deep foundation element itself modeled? That is, the change in stiffness of the pile with respect to the applied moment. Yes, when you perform the nonlinear time history analysis in Midas Civil will automatically take into account the nonlinear effects on the pile. This time in this particular seminar, I just performed the linear analysis, so the stiffness wouldn't change. But when you perform the nonlinear analysis, you can consider that behavior in Midas Civil. Another question by Robert. The question is, does Midas take into account the groundwater table when generating the soil spring? The groundwater table will affect the unit weight of soil, and depending on the groundwater table, you can change the unit weight of soil, and this way you can take into account that thing in Midas Civil. So if you guys have any more questions, please punch in your questions. We still have 10 minutes left. I can do this thing for another 10 minutes, and I think there are some questions that I missed, and you can see my email on your screen, and then you can send me the emails in details, and we can talk more about it. I have a question from Andrew. The question is, how do the results for pile deflection in Midas compare with what you get in a program like LPile? Does Midas use a similar analysis method? Basically, you can say that in Midas Civil, LPile is incorporated. So LPile, group, A pile, you can do that in, you can say that these softwares are embedded into Midas Civil. If you are not performing the soil structure interaction, what you will do is you will ask the geotechnical engineers to give you the soil spring at the location of the support. Now that thing Midas is doing automatically. LPile or group, what they do is they apply the spring based on the soil that you have defined, and again the spring definition is based on the same method that I have talked about. So you can say that in Midas Civil, LPile is embedded and group is also embedded. Now there is a question by Mr. Sadiq Kazmi. The question is, what are the advantages of your software over CSI Bridge? Now that's a very straightforward question. I would say since I work in Midas, I would say that it is the best software, but I'm also a bridge design engineer myself. I used to work in a professional design consulting firm before I joined Midas, and I have personally worked with these two softwares, and I would say that the graphical user interface of Midas Civil is more intuitive and easier to work with, and at the same time it has several other features that CSI Bridge, according to me, they don't have, because I'm not familiar about the latest version of CSI Bridge, but the previous version, Midas Civil has several other features that any other software they don't have, like this kind of soil definition, soil spring definition. Other software they don't have it, and the way you see that in Midas Civil, the pre-stressing in 3D can be defined, and the graphics that you can obtain from the analysis, they are state of the art, and these are some of the items where Midas is better than CSI Bridge, but it's you to decide it. So I have sent you the license of Midas Civil. Install it on your computer, just play around with it, try to do 1 or 2 tutorials, and be a judge by yourself and see for yourself whether Midas is better or CSI is better. So it's up to you. Let me see if I have missed some questions. So I'll just scroll through the questions one more time, and we'll see if I'll see if I missed some questions. Okay, there is a question by Dan. The question is, are the soil properties varied with depth or overburden automatically, or the properties constant, are the properties constant for the depth defined in Midas? This is a very good question, because in the soil, the spring constant changes with the depth for clay, and for some of the soil types it might change with depth, and Midas Civil can take it into account automatically. So this consideration, it can be taken into account automatically, and when you define the ground level based on whatever depth the pile has, whatever the length of pile is, Midas Civil will automatically generate the soil springs based on the embedded depth of the pile. So Dan, it does consider the overburden pressure automatically. So depending on the soil type, if you have clay or some other type of soil, Midas Civil will automatically take it into account. And this particular item, it's also defined in Matlock and RESI formulae, and it has been incorporated in Midas Civil. So yes, it does that. Okay, so I hope I have answered many of your questions, and again, if you have any other question remaining, please let me know through my email, or you can call me. And before I go, I'll just take one more question here. There are two questions I'll like to take. What method of analysis Midas uses? Midas Civil can be used to perform LRFT or LFT analysis, so both are supported. And one other question by George. The question is, how will the seismic soil effects be accounted for? The seismic soil effects will be accounted in two ways. Either you can model the entire foundation and define the nonlinear soil, and then you can perform the analysis. And the second type would be you can just apply a 6x6 coupled matrix that other software generally have, and Midas also has it, and then you can perform the seismic analysis. So the seismic soil effects can be accounted using those springs, or in Midas you have these two options. You can either model the foundation with supports, or you can model the springs. There is another question by Mohammed. The question is, should we consider two opposite direction springs at each pile section to consider passive active situation? Well, in the case of pile, there is no passive or active situation, because if it goes towards one end, it's passive for one side and active for another side. So we just model one spring that contains the stiffness for active in both regions, because active is higher than the passive one. Okay, so I hope this webinar I could give you some idea about soil structure interaction and how Midas Civil can be used for that. Please give me feedback so that we can improve our sessions. I hope I could give you a brief, I know that you guys are already doing these type of designs and you must have considered this type of analysis, but the idea behind this webinar was to share with you the knowledge that we have gathered while working with our clients, and at the same time the technology. I wanted to share the technology with you, the latest technology for performing the solid structure interaction. I would request you all to evaluate our software, to check whether you can use the software in your work, and this would definitely help you to have more confidence in your design. So thanks a lot once again for joining the webinar with us. I wish you all a great day ahead. Thanks a lot. Once again, I'm Nithal from Midas, and I'll be signing off from here. If you have any more questions, please let me know through my email, and we'll keep sending you emails regarding these type of webinars. So once again, thanks for coming. Good day. Bye-bye.